So in a bit more detail what these value functions mean. So here's the state value function. And we've got our return, we've got our state, and we've expanded out for this computing this GT, right? It's just the sum of the reward you're going to get at each action going forward and that discount factor, right? And it's conditioned on being in the state you actually were. So as your robot moves around in the room, it decides what to do. It was actually in that spot, it took an action, and it got some reward. The action's not listed here, so it's very similar to the way we see it in bandits, right? Because the action just sort of happens and it's responsible for the next state, but we don't really represent it. So it's kind of a theoretical way of looking at it, but it misses out the important part, which is what did you do and how did you get there? And that's what we're going to get to very soon. So, but in the the state action representation, you get the same thing, and so you just have an expectation over the sum of all these returns, but it's conditioned on the state and the action. We have a grid world, so we often, any domain we're talking about is going to be something, world, maze world, grid world, pencil world. The idea here is you're moving around this maze, and we haven't told you where you want to get to, but when you take an action or movement, you will get some rewards or penalties, right? In this case, you're just going to get rewards for hitting certain locations. So if you get to A or B, you're going to get these rewards. So if you get to A, you automatically get moved. This is just a particular definition of this game. If you're at B, you get automatically moved instantaneously to B prime, and you get 5 points, 5 reward units. And if you get to A, you get moved here, and you get 10. Right? So that's one part of the reward function. Another part is if you are at some spot and you try to go off the grid, you don't go anywhere, right? So you stay here, but then you get a -1. So you get a penalty for trying to go off the edge. So you should try to learn not to do that. And if you do anything else, you get a 0. So if you go from here to here, you get 0. So no penalties just for moving. Right. So what we're showing here is the representation of the value function after reach convergence. Right. So this is Vs for every state S, and in this case, the states really are just the locations. So we could just number them: state 1, state 2, state 3, state 4, state 5, or maybe you call the states 1, 1, 2, 2. Well, let's make them 1, 1, 1, 2, 1, 3, etc. And then you have 2, 1, 2, 2. Right, so you have a state, but there's only as many states for ourselves. There's 25 states. And we have a discount factor here of 0.9, and we're saying that this is the optimal value function. So after you solve all those equations, this is what you get. And so, right, because when we had our GT calculations, right, we could say being at this state, what's the return for being here, given a certain series of actions. Now we're going to do it based on sampling from all the actions we could take and getting this. Right, so, and the assumption there then, you have to know how are you taking the actions, right? So for the GT things, we know it's given a particular series of actions, right? We got AT plus 1, they're actual actions, and they would literally have been, in this case, like move right, move up, move left, each step, right? So here we're also given the information that the policy we're following is a random policy that just goes random choice that you can go in any direction, right? And you only got 4 directions, so you got 25% chance going each way. And that gives you this table. So in order to get this, your value function, we need to have all of these elements, right? We need to have the rewards, right, which are also given here. We need to have, right, these special states A and B, so the entire reward function and that. we need to have what the actions are. We need to know the space of transitions is deterministic. So from our MDP, that thing that tells us which state we get to next is deterministic. Action is given by this entire set. Our rewards are given here, right? And what else? We have to know the states, right? And the states we know, actually, I already wrote them down. This is the states right here, right? And it goes to all of them, and the number of states is 25 in our case. And we need to know gamma, right? It tells us the way they combine together. So once we have all these, we have all the components of the MDP that we need, and this lets us get the values. So let's make sure we know what this is, right? What is this thing? The value function we're looking at here, right? So in the previous definition, we're talking just with the value function, right? Note that these are the value functions. Oh, I've switched on to mine. These are the value functions for our current policy, right? So for the particular policy we're learning, pi, right? So the series of actions that we're taking as we go forward into the future are sampled from pi. We had this here before, right? That's these value functions. And so it's the one that's based on our current policy. It doesn't mean it's optimal, but then the equation here, this essentially defines an equation for the expected value for that state, right? And for every one of, you can think of that for every state in the system, there's one of these equations because the S would be different. So for state 1, we have the value being there now, the reward we got when we were in that state. And same for SA. So we have equations defining this, but we don't know the form of it fully yet because we've just got an expectation somehow. That's what we have to work towards. So these tables are the solution for those equations, the policy, the values that explain why you took those actions. Well, and in this case, if the policy is random, then the action can be sampled directly, so you can figure out that there's a 25% chance you'd go that way and that way. And so when you got the expectation, you're saying, what's the probability of each event happening? So in the next coming up slide, we're going to show that more explicitly with the probability. But just to kind of put the landscape for those two different types of functions, right, we're using to checkpoint where we are. We're defining these markup decision processes using state, actions, rewards, returns, and time. And you can get a little philosophical if you want, that we're trying to learn a causal model of how things work, but that's kind of more complex. But the goal is to optimize these expected returns using this particular model of discounted sums of future rewards. So you can have other ways of modeling that. The gamma discounting for the future is only one way to do it. And we got those 4 value functions with the state and action, as well as for the optimal and for our own policy. So for the optimal value functions that we defined, those would look similar. When we say it's optimal, here's a bit of what that means, right? For any particular policy you could follow for that given MDP. So, this definition here, all of these parts, like I said, those define the MDP we're using here, right? All of these components, the states, the actions, the dynamics, the reward, right? For that particular MDP, then you can have a policy for what to do, and when you're in some cell, which way should you move? And some policies are better than others, right? So we can use the Q pi and the V pi functions to give you the value of following that policy into the future, because it would tell you what to do if you're in a certain cell in a certain state, and then you'd follow that forward, and you can compute your value discounted forever down for each state. So if there's all this property that some policies are better than others, there must be one that's the best, right? Or a set of them that are the best. Those are going to be the optimal ones. So the optimal policy is just going to be the one that's greater than or equal to all the others, right? And so you could define them this way. That's no matter what state you're talking about, this value function v star gives you the highest possible value for that state. And it uses the policy that would get you that, right? Because no matter what policy you have, remember for that grid world, for essentially every state, there's a unit here, right? If that's cell, let's say 5, 6, 7, 8, that's state 8, right? We'd say the value of state 8 has some particular value, right? And no matter which policy you have, if you had a policy that was optimal in all the others but not that, you could just swap out that part, right? Say it's going to be the policy that tells you what action to take there. So you can always construct this, and it'll always be there is an optimal policy that's better than all the others, or a set of equal ones that are better than all the others. And the same policy would have the maximum action value function. And as I said, there is another way to write this where once we have the probabilities in there that we can write, you can write V in terms of Q. So maybe try to think about how you would do that now if you haven't read ahead yet. It's not that hard. So if we look at the optimal one, this would be the greedy one step ahead policy. So given the optimal V star, so here we're showing that same MDP, but here we've got V star, which is the following the optimal policy, the ones that get the highest return overall for every state. How much return would you get, right? And it's gonna, these numbers are higher, right? Because in the other case, we were showing just for some particular policy pi, and that was the policy that randomly went in every direction with equal probability, right? So at 1/4, every direction was equal, right? This is the policy that's optimal, which says if you're in this, you should go these ways, right? And so if you had QSA, you'd be able to see that which direction is better than the others, right? So for VSA, it rolls it in and says, well, here's the value of being in this state, because it'll assume you'll follow these arrows. If you have QSA, you'd have the value for these two different outcomes, and you could choose, well, for all 4 outcomes, right? But for the number here and here, that would be less than these ones that have been chosen. So what this kind of graph shows is the optimal policy. But you could draw any policy this way, right? The policy that we were given, our original pi, has every cell with this kind of 4-way arrow on it, right? Assuming that you basically, I guess the assumption here is that each arrow has equal probability under pi star for that state. Right, and so this kind of makes sense because this is the policy that if you find the optimal ones, like, well, if you were here, you should make your way up to A so that you get the maximum reward. If you're near A, you should make your way there or climb up so that you essentially come in this way, right? You want to get to here, right? And if you're down here, you want to go that way and hopefully cut across. And you don't mind cutting across here because you're going to get a 5 and then you'll make your way up. But you're essentially, everybody's trying to make their way to A, but they don't mind if they cut through B on the way, but they're not going to go out of their way to get to B because A is always better, right? And they're not going over the edges, right? Because remember, we get a penalty for going over the edge. The optimal policy never goes off the edge of the graph, which is what you'd expect, because that's just pure waste. You move there and you lose it. So the optimal policy couldn't possibly contain that. That just makes logical sense. Right, and so this, we said this before, if you have QSA, then you want to get the optimal policy, you can just read it off, right? Because for one of the particular situations, you'd have these outcomes, right? So if we say we want to do this location, then QSA is going to be an array of 4 values, and let's just assume that our directions are 1, 2, 3, 4. Then directions 1 and 4 are going to be the best, and they're going to give you this some reward, although we don't know the return. Now I'm thinking through this. It would be, okay, I'm just guessing here, we're going to work it out. I'm going to say it's 8 because half and half, chance of going there, maybe 16. Okay, we'll have to work out the number, but it's going to have a high number here and then a low number for the other ones, right? Because these directions are going to be lower. But these will give you the same one because it did say they're equal. So whatever they are, they're going to be the highest. So how do we compute these in a more practical way? We're going to get one of probably the most important equation, which we're going to see many forms of course, is the Bellman equation. And it's really a family of relationships, but it ties together all these different parts of the MDP that we've seen so far. So we're familiar with this return relationship. We've got the return we're getting every step. It's discounted the future. So you could represent this recursively, right? I know everyone loves recursion, and reinforcement learning is all about recursion, but only really in this relationship. So you can see this defined by saying that the return that you get at this time step t by following your policy into the future can be defined based on your return of the same form, but the next step. All right, so if we assume that g has this form, we're just using gt plus 1, right? So once you're there, you can do the same evaluation of your future rewards and discount them. They're embedded with each other. That's why having this discounting go up by 1 in the exponents and time steps go up by 1 makes this nice sense. So if you do that, we define the expectation of our value function as that, but the expectation assumes there's a probability in there. So we haven't really seen how you get that probability, and here's how it is. Here's how you get it. We had our transition dynamics, remember, from the MDP, and so that's the probability that we're going to end up in some state S prime, given we're in the previous state and we take an action, and we'll get some reward from it. Not all formulations will have this. Usually this is not present because you get the reward directly from the system, but you do get a reward, and then this probability says how likely that transition is to happen, right? So in our deterministic grid world with the robot, it was deterministic, right? So it's 100%. So this is always going to be 1 in that domain because it's deterministic. You move to the right, the world moves your robot to the right. You try to go off the edge of the world, you don't go off the edge of the world. All probabilities are 100%. Obviously, in most domains, that's not true. We'll get to that. But then for the rest of it, we're doing an expectation, right? So here's your probability. It's the probability, because what's an expectation, right? This expectation has to be the sum over some probability of something involving s and t and pi, right? That's what this has to be, some kind of function, a probability that gives you something. I'm just putting a dot here of that, right? And well, probability of really an action. And then we know that for some action, we'll get a reward, right? I guess in this case, we're just talking about the reward. So we know that for some, and we know that for some action, we're going to get a reward at that time step that'll be worked out by this function. So if we have a reward function that takes s and a, then that would give us this, right? And the MDP usually has to have that defined. So, but there's our sum over probabilities of the rewards, right? And then we put the discounting in here as well, where the discount is based on t minus 1 in that case. So if we're summing over all the values of t, that's what would happen. So that's just in general. Specifically, this is the way we'll represent it, because you have some probability and you get the reward, and you're going to add a discount of the entire function, right? So here's reward plus discount factor of the rest of the function. That's what's happening here. But there's no probability in this return, right? What's the likelihood that you're going to get this reward, or you're going to get this one, right? The probability of getting these rewards depends on the probability of, first, of you choosing a from pi of s, right? So if you're in your state s, you sample some action a, and then you get a certain reward. So this r rolls into it all the probabilities of how it happened, right? What we really want to do is break those out, make them explicit, so that we can predict and learn models of each of them individually. So we got the model of the probability kind of model of the dynamics, right? We got the probability of the policy. So this is the probability that we will take this action given this state. And this could be a deterministic function, in which case it's just going to be 1 for the one you took and 0 for all the others. And this is going to be the dynamics of the world, right? Obviously, I said this is 1, but it's going to be 0 in all the cases where you don't take that, right? So if s prime is stepping off the edge, right, and s is, or s prime is showing up in any cell that is not right beside the cell you're in, right? And cell is, s is some cell. So, you know, if we had that, you have to think that every possible state in this system has its own value there, and you can iterate through all possibilities. So for this one, the probability of you ending up here, given that you start here and you take some action, that's 0, right? Because there's no way to get there. So it's not one step, and it's not that particular case A and B where you jump down. Right? So all the things that are impossible are just 0. And then the ones that are possible, you actually get a reward, and you actually have a discount factor. But then for this, we say we're going to take this trick, right? That we know that in the future, we're just going to do the same thing again. So you use the same definition, your own value function, and so you get this recursive definition, right? So we'll have it here again more cleanly. So one way to visualize this is to say you're in some state. It could be in either direction. For v, it's going to be s, like this. And you have all the actions you could take. You have these backup diagrams. And then after you take that action, you get some reward, and then you end up in the next state, right? And for the Q state value functions, the root would be that you're taking a state in action, you get a reward, and then you're going down. to the next state in the actions. So really that's what's happening here. You're building out a recursive tree over all possible paths, and some algorithms explore this tree explicitly and try to figure out where's the optimal one. So you go down the tree, and at some point you find one with a very high reward, and you go backwards and you say that's the path, those are the actions we should have taken. And other ones do a breadth first search that say, let's look at all the actions for the next step and pick the best one, and just remember that. So this main structure gets used in all the algorithms in reinforcement learning, and you've got this recursive approach where you're using your own function to define it, but note that it is for a different state, right? You're saying, given the next state you would arrive in, you can look that up, right? Because V is really a lookup table, right? And you're going to model it as a lookup table at the beginning, and it has values in it, right? I guess we would say that that's the state, right? And so whatever value you got in here, it's going to be an actual number that represents your current estimate of the value of being in that state. Okay. So if we go back to the grid world, now we can see where these functions come from. This is the value function that we have been talking about, and each one of these values is computed by, has a relationship defined by recursively referring to itself as it goes forward. So that was for your particular policy for V pi, but for the optimal policy, V star, we have the same idea, right? So in this one, we're saying, and here's the representation I was talking about before, we can say that the optimal value function V, where the state, is just, if you knew the Q function, then you just have to go through every state, find the best A, and choose that, right? So the table V is really just the max for each row of Q, right? Because you could say that the Q function is more like that. And for every state, you've got all the actions you can take. Say there's 3 actions, and maybe they've got different values, right? And you'd always take the max one, right? And V star would just be all of the max values here. But it's an expectation just like the other one, so we can expand that out and say it's really to be the reward, the return for that, plus its own value function, but for the next state, right? Whatever state you're going to end up in the next step, because this is one time type step in the future. And then to take away the expectation and actually represent the policies explicitly, we need to know the dynamics of the system. So what is the probability of transitioning from one physical state of the system to the next? Notice here we don't have pi, right? Because we don't care what your policy is. We're just going to take the best action, no matter what, from here, right? So we're going to evaluate the state, and V already knows the value of that state, assuming you always took the best action, and so you just use that, right? But you could always replace, there's many forms of the Bellman equation, so if you ever have a V star there, you could always have max a Q star instead, right? If that's what you have available, then that's what you'd be using, right? Because you can just read it off there, and that's how you can compute V, right? In fact, in this form, if you compute the Q first, you can compute the V by running this equation for every state and taking the max. And we represent the backup diagram here a bit by showing a function across the actions. These diagrams don't get used that much, but they help with intuition of it. just to make sure you know what's happening. And for it to be the optimal equation, it has to be kind of the fixed point of this, right? And it really is, once you write down these equations for each possible state, you're talking about the unique solution where the values satisfy the maximums for all the equations at once, right? So for Q itself, we don't even have to. So here we're taking the max A at the back. Here we're actually just going to store it for every Q and A. So Q star A is also recursively defined in terms of itself, but now you don't need the max here because you're just going to actually store the S and A, which are the parameters, and compute it for each one, right? So if we represent that here, we're just going to be kind of having a function, taking a max over the children in a sense, right? And remember what's happening here. You're at some time step t, right? And then you take an action at, right? And that's a. And then you get a reward, which we'll call RT, which we're not explicitly denoting it here. And then, I guess in this, I'll use a different color after. You have another state, st plus 1, and another state, at plus 1, and then you would have another reward rt plus 1, although that's not what we're talking about right now. So in the notation we have above here, this is S, this is A, this is R, this is S prime, this is A prime, and we don't get here, right? We just stop at this point and say, I'm not actually asked for the reward, I'm just going to say Q star, because Q star rolls in all possible future things forever into its value. That's what it is, right? That's why we're doing this dynamic programming, right? We're storing the value here of this entire equation and then iterating, and we might go through and update a particular SA many times, and it'll get closer and closer to the optimal. That's kind of the beauty of the approach. Okay. So how do we solve these equations? That's the next focus for the next week's kind of topics and the rest of the course, kind of setting the groundwork now of what the problem is. But how do you solve them? There's many ways to do that. This Bellman equation is really the core thing that we're using to talk about it. We need to have a few things in order to make that possible. We need to know the dynamics of the environment if we want to solve it perfectly. We have to have enough computational power, and we need this Markov property, right? So we talked about Markov decision processes. We need it to be true that the only information you need to take the next step is everything that happened in the last step, right? If you need to remember things from 20 steps ago that aren't represented in the current world, or you don't have some memory, then this won't work, right? Everything has to be represented in the state. The state could include memory or notes you've taken about the past, but it can't require a link to the past. And if you think about navigation or something, you know, that's definitely the case, right? Because it might seem relevant to you that you took a right turn there and a left turn there and you got to this spot, but all that matters is where you are right now in the space, how much fuel or power you have left, what's your goal. There's many ways you could have got to this destination, and the only thing that actually matters is where you are now. So the main point of this is that trying to solve this exactly is complex. That's why control is a kind of an optimization or big complicated fields with lots of their own tools. But in reinforcement learning, we have trouble having this value, right? The dynamics are hard to get, they're not available right away. We have the Markov property, but we're usually going to be making approximations to this because the real world is too complex. But we're going to use this Bellman optimality equation and approach the optimal policy approximately. These are all the things that you should be familiar with by this point. And like we have some of them we have explicit lectures on, some of them you can read through. But if there's any parts of it that don't feel complete, we can go back and cover them in the live office hour things or on Piazza. Optimal policies, need for approximation, that's just that last point. Yeah, so make sure all these concepts kind of make sense, and then I'll move on to the next things, which is how to solve this. See you then.